Question 2.1 is saying define the cumulative compound generator. So we can define it as a generator in which series and the shunt field coils are connected in such a way that the fields support each other to produce more magnetomotive force. Or we can define it as a series, a generator in which the series field winding is connected so that the ampere turns act in the same direction as those of the shunt field. Right, so that's the definition there we can give of the cumulatively compound generator. Right, let's go to 2.2. Draw a neat, fully labeled circuit diagram of a shunt wound generator. Clearly show, number one, the field windings, the armature, and the load, which means these need to be indicated on the diagram. Right, so number one, we can start with the armature, this side. Right, there we go. Right, and then we go to the field windings. So we have the field windings at this point. They are the field windings connected in parallel with the armature. And then at the terminals, we have our load, as they have been told to indicate also the load. So there is the load at the terminals. Right, so basically, these are diagrams. So we can now label it. The main current being the armature current because it's a generator. So we have IA this side. So of course, at IA, we can also put the polarity, positive, negative. Then of course, we can indicate the resistance of the armature RA, and we can label this as the armature. We indicate the armature here. So we are now labeling it. And of course, this is the IA there. We have I shunt going in this direction, right? And of course, here we can have the field, the shunt field, right? We can indicate this as the shunt field, right? Field, right? And then we have the load, right? Right here at the end of the load, we can also indicate terminal voltage again, this side. This is where the voltage is also lying. Right, apparently that's our load there. And of course, we label the current that is going to the load as IL, that marks our current there. So that's basically the shunt field generator. Right. Let's quickly go to the next question there. The next question is saying the terminal voltage of a 4-pole wave wound generator is 220 volts. The armature current is 80 amperes and the armature resistance is 0.45 ohms. Calculate the speed in revs per minute if the number of armature conductors are 680 and the use for flux per pole is 20 milliweber. So we have to use the formula E, the generator equation, is equals to 2p phi Zn over 60 times C. Right. This is the formula we are supposed to use, where E is the generated EMF, 2p, P is the pair of poles, phi is the flux, Z is the number of conductors, and the N is the speed over 60 times what? Times C. Okay, so that's the formula we are supposed to use there. Right, so in using that formula, unfortunately, we do not have E, the generated EMF. Where are we going to get it from? We can first calculate it because we've been given the terminal voltage there to 220. And of course, we have the armature current and the armature resistance. So according to the information that we have, this is a shunt machine. That's a shunt generator there. So we can use the formula E is equal to V plus IA, RA, remembering that our main EMF, our main voltage is the generated EMF. So in a generator, it's going to be V plus, because these are now the potential differences that we're having, right? So, so that's IA, RA there. So let's calculate E, the generated EMF. So we are going to say 220 that we've been given there plus, right? IA we have been given as 80 multiply RA, which is 0.45 we've been given. So if we multiply that, what are we going to get? Punching on the calculator is going to give us 256 volts. 256 volts. Right now that we have E, the EMF, We can come back to this formula here and make n the subject, because we are calculating the speed. So we can make that n the subject. So how are we going to do that? First, we multiply both sides by 60c. The denominator we are having multiplied by 60c, right? So it's going to give us, upon multiplication, we are going to get 60 CE is equal to 2p phi Zn. This is what we now have. But then we want to make n the subject, so we can divide now by 2p phi Zn. 2p phi z divide by 2p phi z. So we end up having n is equal to, right, that's going to give us 16 CE over 2p phi z. So we can therefore substitute all these other variables that we are having, right? 60 multiplied by c. C is representing, in a wave is 2, and apparently that c is the number of parallel paths between the positive and the negative brushes. For a wave wound machine, it's 2. Then for the lap wound machine, it's 2p. So apparently this is a wave wound machine, we have been told. So because of that, it's going to be 2. So we can substitute a 60 multiplied by 2 multiplied by E, the EMF, we've just calculated it, and we got 256 there, right? Divided by 2p. P is the pair of poles. So if we've been given, like in our case, we have a 4-pole machine. So our pair of poles are going to be 2. We are dividing that by 2, right? Multiplied by flux. The useful flux people were told is 20 milliwebers. Milli is times 10 to the power of -3. That's one key important thing again to take note of, right? Multiplied by the number of conductors, 680. So it's very critical. I often advise, list the data first before you answer the question. It serves you very, very well. Right? So we are saying this is what we are having. Of course, we are dividing here. We are dividing. Upon dividing 60 times 256 divided by 2 times 2 times 20 times 10 to the power -3 multiplied by 680, what are we going to get? Of course, punching that on the calculator, it's going to give us 564.706 revs per minute. This is what we now have. So apparently that's the speed in revs per minute. We have the speed in revs per minute, right? Just like that.